You are given an array A, and you're supposed to construct it first by inserting elements into the array according to their index positions from left to right. Okay, so we can do this. So the number that we are getting here, let's copy it. Okay, so first you have 2 and then 10. So 2 comes in to become the root. 10 is larger, so 10 will go to the right. 4 is larger than 2, smaller than 10, right? So 4 is going to come here. 7th, 19th, there's 19 here. 19 is going to go to the right of 10. 5, so 5 is larger than 2, smaller than 10, larger than 4, smaller than 7. 8, 11, so 3, and then finally 15. Right, so you will get a 3 that looks like this. So we're going to insert it one by one. 15 should be, okay, right here, right? So means the left child is 11, the right child is 15. Okay, all right. Then the question is asking for pre-order and a post-order. So what is going to be the pre-order? So pre-order means parent, left, and then right. So parent means the root first, nothing on the left. So then we go to the right. The right is 10. Then you go to the left first, which is 4, and then the left, and then 7, 5, 8. Now we have done the left side now. We can then go on to the right, which is 19, 11, 15, right? So this is the pre-order. So for the post order, we have left, right, and then parent. So we start from the root. Root says do my children first. So you go to 10. 10 says do the children first. 4. So the first one we'll visit is 3. Now we cannot do 4 yet because we have to come here first. And then we need to do the children. So that's 5 and 8. And then 7 and then 4. Now by now we have done the left side of 10. So we can go on to the right side of 10. Starting from the children is 15, 11, 19. Then we have 10, and finally we have 2. So left, right, and then parent. Okay? Now, by now it should be clear how to construct a BST. BST doesn't come about because we have a regular 3 and then we sort it into a BST. BST comes about by inserting the elements one by one, and each time we're going to preserve the ordering within the BST. Now, the other part of the question is saying that we would like to create the following shape, which is kind of zigzagging, right? Now to create this shape, we need to insert the 3 elements in a particular sequence. And the sequence is going to recreate or reconstruct this shape. Now this shape has a root. So what can we tell about this root? Is there any particular property of the root node here? Does it have any child? Yes, it does, right? It has one child, which is on the right child. But it doesn't have a left child. So it doesn't have the left child, it only has the right child, and all the numbers are on the right. So if all the numbers are on the right, it means that this particular root must be the smallest one, right? So it means that it must be the smallest element within the whole array, which in this case is 2. There's nothing on the left, everything is larger. Now, once you go to the right, you realize that the child of 2, so must be larger than 2, because it's on the right, but itself doesn't have a right child. Every child is on the left, every descendant is on the left, which means that for this particular node, there is nothing larger. So it must be the largest one then. And the largest one in all of the array is 19. Now, then we go to the left. Now, this number is definitely larger than 2, because when we start from the root, we have to come from the root to the right. But once we get to 19, we go to the left, so it must be smaller than 19. But this is again smaller than anything else that remains in the array. So then it must be the second smallest number. And this one then will be the second largest number, and so on. So to recreate this shape, you essentially have to create a tree by first taking the smallest element, and then the largest element, and then the second smallest, second largest, third smallest, third largest, and then the fourth smallest, the fourth largest, and so on, right? So then once you have a sequence, when you insert it into a binary search tree, you're going to recreate essentially this same shape. Now, this shape is still considered linear. I mean, it doesn't look like a straight line, but it's linear because there's only one node per level, which means that in the worst case, you still have to visit every single node at every level in order for us to know whether we can find an element or not. So that means that for this kind of tree, the searching will still be O(n).